Okay, now for our last one of Unit 5, catalysis. So we've mentioned these before, a little bit in the more of the um, energy diagrams that we've looked at, but I want to go through just some of the things that might come up in the words they're talking about and using throughout AP. So catalyst, something speeds it up without being consumed, and consumed means like bonded into something else at the end. It's left over once the reaction is completed. Enzymes are a natural catalyst in biological reactions. And remember, homogeneous is present in the same phase, heterogeneous is present in a different phase. So they work by having the alternative mechanism for reaction. So that means they may have more or less steps than the original. But they actually usually look at lowering activation energy and or increasing the number of effective collisions. So they're consumed in an early mechanism step and then remade in a later one. So when we have something like ozone react with oxygen atom to produce two oxygen molecules, this is a very slow concept. Chlorine, though, can act as a catalyst to get things moving, and then you can see it's released in the end. So this is a big role that we have in our ozone layer, that this chlorine atom plays this much faster role in breaking down ozone. So types of catalysts. We have the idea of reactants and products. Same phase, different phase. So a catalyst could be like a solid working to have a gas react. Lowering activation energy because of the catalyst. So again, this is the way it would look based upon there. It doesn't make it happen any faster per se. It would make it happen in a time sense faster. But as far as an energy sense, it doesn't change the delta H, the change of enthalpy for the reaction. It just lowers the activation energy. So things like stratospheric clouds having ice crystals can catalyze it because it gives it a place for those chlorine chemicals to deposit. So again, normally this would be the energy pathway. Transition states, so you can see it takes on multiple steps instead of just one, gives it a lower activation energy barrier. Again, I like showing these visuals because sometimes you need to draw the visuals or interpret the visuals as well. They really increase the number of effective collisions. So when we think of the kind of distribution of energy of the particles, the idea is that in a catalyzed area, you're lowering the activation energy. So when you lower the activation energy, you're going to include more area under the curve, which means there's a higher number of collisions with that given energy based upon that distribution of energy from the system itself. Now, again, the molecular interpretation of factors concerning catalysts. In a homogeneous catalyst, they react with one of the reactant molecules to form a more stable activated complex, which then will help lower activation energy. So this is given in the sense like here, where we have all gases, right? All gases, homogeneous, this gaseous one creates an intermediate, and that intermediate is going to be able to be used. So because it goes to an intermediate, it lowers energy. Back to here. Heterogeneous hold one reactant molecule in a proper orientation for a reaction to occur when the collision takes place. Sometimes they also help to start breaking bonds. That's a little less common. The idea is that they hold something in an organized way in order for a collision to take place. So let's look at just an example. So platinum is often used to have carbon monoxide, nitrogen monoxide adsorbed onto a platinum surface. This goes on in your catalytic converter, a especially expensive box that you find in your exhaust system. So because it's charged and has this, we have the ideas that the things that are less electronegative are going to be attracted to it. So as they come down, they're going to be arranged in a particular pattern. And so as they move on the absorbed reactants on the surface, they can start to pair up. You can see how we have organization of carbon dioxide, organization of nitrogen, and again, carbon dioxide. once they've gotten the reaction on the absorbed surfaces, they can escape because now they're no longer attracted to it. They desorb, they come off because now they have different attractive forces than they had before. You can see these are all nonpolar as opposed to all of these being polar. So the idea is that they're attracted polarity-wise. They become close enough to overlap orbitals and therefore can react. And now they're nonpolar and boop, off they go. There's another example of an acid-base catalyst. This is just an example so you can start seeing it in advanced areas. But again, we're not going to have anything this complicated in talking about acid-base catalysts. So normally, this one right here, this molecule, would react in a longer way to create this here. It would break apart to create this molecule here. But you can kind of see the factor that you have this OH reacting and that the carbon-nitrogen triple bond, how does this hydrogen come around? So this would normally break down to this. However, what we occur is that when a base comes around, like a hydroxide molecule or hydroxide ion, it attracts this hydrogen off, now creating this very reactive area to where now this is going to come in and share the oxygen here, and that this water molecule can now come in and attract these valence electrons from here to make this hydrogen. So to go from this process here without the base to here, again, the base wouldn't be present, takes a lot longer time. But if you have a base come in, takes the hydrogen, giving you water, and this ion here, the water collides with here, creating the HCN molecule, and then now this comes in and shares a double bond. So this would take a lot more without the base catalyzing it. Over here, this epoxy ethane to make ethane 1,2-diol. Don't get hung up on all the naming. But acid comes in, H plus ion, and creates this to be a lot less stable. Water's given off to where now this can break apart. Again, taking away the acid, the idea is a subtraction of it because it gets removed, then creates this compound here. So it goes through a lower energetic state to get here because the hydrogen acts as a catalyst and the base acts as a catalyst. The last part, binding to the particles and then being released. So something like a CFC molecule, chlorofluorocarbon, that's what CFC stands for, undergoes hemolytic cleavage upon exposure to UV radiation. Essentially, UV comes in, it breaks off. Now this chlorine atom comes in and starts reacting with the ozone, breaking it down to the ClO and oxygen. Next, the ClO comes with another one, creating this C2O2. And this is very reactive though, and then separates two more times. So it separates here and separates here, leaving you with O2 because this will become a double bond again. And then you have extra chlorine atoms that'll kind of cycle back in. So this highly reactive process goes under and continues to go, propagates a chain, going back to 2, breaking up more and more, until it eventually bonds with something else, probably like 2 chlorines, and then is able to now be more stable in our environment. So this binding is, again, another action of how these are kind of used. You see some intermediates are used in order to get to our final idea of ozone being released. All right, so I hope this kind of finishes our area on Unit 5. Let me know what kind of questions you have, and take care.